All right, let's get into the solutions. As always, if you enjoy this content, give us a like and subscribe. So we've got a particle that's moving in a circle, and they give us the equation for the angular position. And they want us to give us the speed, but in speed they didn't ask for the angular velocity. So we can get the angular velocity by taking the first derivative of this equation, and that gets us 26 radians per second. But here's the trick, because I think most people are going to go straight for this 26 meters per second, but that's 26 radians per second. So we need to use V equals rho omega to be able to convert from radians per second to meters per second. So we multiply through by 2 the radius to get 52. Okay, in this one, we've got a similar type of situation. We have this turntable, this disc that's spinning, and it has an acceleration equal to alpha. And they want to know what's the angular velocity after it has made one revolution. Well, one revolution is 2 pi radians. So all we have to do is our omega final squared formula. It started from rest, so we have 2 alpha delta theta, and delta theta is 1 revolution, so that is 2 pi, and then we just take the square root of both sides to get the square root of 4 pi alpha. Okay, in this question, we have a 10 kilogram sphere and a 5 kilogram sphere on either side, and the rod doesn't have any substantial mass to it. So the question for the first question is, which of the 5 lettered points represents the center of mass of the sphere-rod combination? Well, if we look at this, we see that there's more mass on this side than on this side. So we know that the center of mass has to be somewhere pushed over in this direction between A and C, so that would be the answer of B. And the next question said that the sphere-rod combination can be pivoted about an axis, and they want to know, it's through these lettered points, through which axis point is the moment of inertia going to be the greatest? Well, where are we going to have the most amount of mass furthest from that radius? Because we're dealing with, in this case, mr squared. So we want the greatest mass the furthest from the pivot point. So if we put the pivot point at the 5 kilogram mass, then we get 10 kilograms as far away as possible, and that's the maximum value. This is a tricky question, but we went over it when we did conservation of angular momentum. So we have an ice skater, and they're spinning with their arms out, and they pull their arms in. So there are no net torques on the system. There's no external net torques. So therefore, angular momentum must remain the same. So we know it's either C or D. But when we deal with the kinetic energy, the person has their arms out like this. They pull their arms in. So there is a force that is parallel to a displacement. So that means work is done, and that work turns into rotational kinetic energy. So the rotational kinetic energy increases. In this one, we have a cylinder that is rotating with a constant angular acceleration, so it's increasing its angular speed. They give us the moment of inertia. They tell us it starts at rest, and they say at 2 seconds, its angular velocity is 1 radian per second. So the first question is, what is the angular acceleration? So this is just a rotational kinematics problem, and if we look at what they gave us, we said that the initial angular velocity was 0. We're looking for alpha. This took place over 2 seconds, and the final angular velocity was 1. So it's just 1 equals alpha times 2, which is a half radian per second squared. The second question says, what's the angular momentum at 2 seconds? Well, we know that the formula for angular momentum is I omega. They gave us I, which was 4, and at 2 seconds we know it's going 1 radian per second, so it's just 4 times 1. And then the last question is, what's the kinetic energy at 2 seconds? Well, that's rotational kinetic energy. So that's 1/2 I omega squared. We have I is 4. Its angular velocity is 1, so it's just 1/2 times 4 times 1 squared, or 2 joules. In this question, we have a particle moving along with m times v. So we know its momentum, but they say, what is the angular momentum with respect to the origin of the system? Well, we need that mv not across here, but what is perpendicular to it. Remember that L is equal to r cross mv. Well, what's r in this problem that is perpendicular to this mv? That's a. They define that as a. So that would be amv, but they rewrote it as mva. In this one, we have a stick, and they tell us that the moment of inertia of the stick about its center is I naught. And then there's a particle of mass m that's attached to one end of the stick. So it looks like this. We have the stick of I naught, and we have this ball that's sticking to it, which is half the length of the stick because it's at the end. And they want to know, what's the moment of inertia of the combined system about the center of the stick? Well, that's going to be some new I, where we have to add the moments of inertia of the two objects. Well, the stick they're giving us as I naught, and the ball is mr squared. But how far is r? Well, r is from the center of mass, so that's L over 2. So that's going to be L over 2 squared, and that just becomes 1/4 ml squared plus the moment of inertia of the stick. This one's kind of tricky. We've got mass 1 moving along with speed v towards a stationary mass m2. So what's happening here is we have this mass 1 and this stationary mass 2, and the center of mass of the system, we don't know exactly where that is. Let's just say it's here. As this mass approaches mass 2, the center of mass is moving of the system. After, let's say they stick together, then we have m1 and m2, and the velocity of the center of mass moves off with these two objects. So if we can find the velocity of the center of mass after the collision, we know the velocity of the center of mass before the collision. So to do that, all we have to do is linear momentum and say the momentum before of the system equals the momentum after. So we have m1v, that's the v that the first mass is moving, equals the combined masses times the center of mass that's moving. And isolating, we get vcom equals m1v1, or m1v over m1 plus m2. In this question, we have a light rigid rod. In other words, they're telling us that the rod has no substantial mass, and they're giving us these two weights on either side. So you can see that this thing is most likely going to start to rotate in this direction. So the question says the rod begins to rotate with what angular acceleration? Well, what's going to angularly accelerate it? That's going to be a net torque. So we can do net torque equals I alpha equals the two torques added together. The problem is, what's I? So we have to do a separate problem just to figure out the new I. So what's I of the system? Well, that's going to be mr squared of this plus mr squared of this. So that's going to be 3m times L squared plus, then we have m times 2L squared. So when we add those all up, we get a moment of inertia of the system of 7ml squared. So now we can go back and put in 7ml squared for our moment of inertia of the system times alpha, and then we look at our torques. So what torques do we have? Well, this is producing a torque of 3mg times L, and this one's producing a torque in the opposite direction, so I made it minus, and that would be 2L times mg. And all we have to do is add those up, so one of the L's crosses out, the M's all cross out, and we're left with 1/7 g over L. Okay, this is a rather long problem for a multiple choice, but if you know what you're doing, it's not too bad, because all it is a conservation of energy problem. We have a bowling ball rolling along. They give us the moment of inertia. That's a 2/5 mr squared is a solid sphere. It's rolling without slipping, and then it goes up a hill. So what's the height of this hill? How high up the hill can it roll? So we're going to do the energy initial equals the energy final. And what do we start with? Well, we start with rotational kinetic energy and translational kinetic energy. And that's all turning into PEG. We know KE rot is 1/2 I omega squared. And translational kinetic energy is 1/2 mv squared. And that's going to turn into mgh. Now remember, we've done this many times in the lessons, that we can say V equals rho omega, rearrange that and say that omega squared is v squared over r squared. This is true for an object that's rolling without slipping. So we can sub that in here for v squared over r, and then just put in our moment of inertia. Our masses will cancel out, and we do the fractional algebra, and that leaves us with 7/10 v squared over g. In this one, we're given an object in which torque is being applied. So the initial torque is very simple. It's just r cross f, which is L cross f. So that's it. And they want to know which one of these diagrams also has the same torque. Well, this is double the torque, but the torque that's acting perpendicular is going to be the adjacent side, so that's going to go with cosine. And cos of 60 is 0.5, so 0.5 times 2 is 1, so that would give us L cosine 62f. That would be, again, L cross f. Okay, rather than rereading this entire problem, I'm just going to tell you what's happening because you probably read it. These are spinning at the same angular velocity, and they want you to compare the moment of inertia of the top to the moment of inertia of the bottom. So what's the ratio of the angular momentum? Well, that's going to be directly proportional to the moment of inertia. So how do we do that? Well, for the top, we just have mr squared plus mr squared. Our r's are l's, so that becomes ml squared plus ml squared, so that's 2ml squared. And on the bottom, we have mr squared plus mr squared. That's going to be 2m times 2l squared, and then we do that again, which gives us 16ml squared. So this is 1/8 of this value here. And again, that's because the moment of inertia is directly proportional to the angular momentum. This problem looks super complicated, but in actuality, it's pretty straightforward. All they're asking us to do is to find the total torque, the net torque. So we have all sorts of torque here. This torque is going to be 3r cross f, and that we'll call positive torque. And these other torques are trying to rotate it in the other direction, so that's going to be 2r cross f. This one's going to be 3r cross f, and this one is also 3r cross f, because they're all perpendicular to the radii. So all we have to do is add them up. Here's our positive one at 3r cross 2f. And then our other torques are in the opposite direction, so we just put in the radii and the forces. When we add them up, we end up with 2rf. Now, I did this with my clockwise rotation being positive. This came out negative, but the question said what's the magnitude, meaning only what's the total value. In this question, we have a wheel, and it's rolling along without slipping, and they tell us the angular velocity of the wheel is omega. What's its linear momentum? Remember that if it's not slipping, then the velocity of the center of mass is equal to r omega. So it's a pretty simple problem. We just do p linear equals mv com, and then sub in our r omega. And they rewrote it as m omega r, even though it's really mr omega, but it's the same value. In this problem, we have two different masses that are producing two different torques. And the question says, when will it be in static equilibrium? Well, that's what's going to happen when the torque that's produced by this mass equals the torque of the other mass. Well, when is that going to happen? Well, that's going to happen when m1g, so that's the force of this one, which is acting at a radius of a, is equal to the torque 2, which is going to be m2, which is acting at radius b. The g's will cancel out, so we're left with a times m1 equals b times m2. This one starts easy, then gets hard. So the first question is pretty straightforward. We have a wheel. They give us the rotational inertia is I, and the angular speed of the wheel is increased from 0 to omega final, and they give us the time as uppercase T. And the question is, what's the average torque on the wheel during this time? So the net torque is going to be equal to I alpha. And we're going to say this is for constant alpha. So that would give us the average torque. And the problem is that we don't have alpha. But we can get alpha from rotational kinematics. It started from rest. Omega final equals alpha times t. So that gives us alpha. Then we just sub alpha in here. And that gives us a net torque, which is also the average, I omega final over t. Now, the second question is much more difficult. What's the power? Well, we have to go back to our old definition of power, which is work over time. But if you remember, there's a mini derivation where power is also equal to force times average velocity. So the first trick of this is that we have to find the average. Now, it started from rest, so that would be 0. So our average velocity would be the final divided by 2. However, we're doing this for angular velocity, so we need to sub in our omega final. That's 0. So our average velocity is r omega final over 2. So that gives us F times r omega final over 2. But look at this. F times R, really R cross F, same thing, that's our net torque. Well, if that's our net torque, we can take our answer from part A, number 19, and sub that in for our net torque. That gives us I omega final over T times omega final over 2, and a final answer of I omega final squared over 2T for the average power. In this question, we have a sphere, and they give us the moment of inertia I. And the first part of the question is really just a trick question. It says that it slides to the bottom, but what is its speed, v-com, if there's no friction? Well, if there's no friction, it's a super easy problem because that's the same as a block sliding down a hill. The sum of the energy initial turns out to the sum of the energy final. We have no rotation, so it's just PEG becomes KE, which is mgh equals 1/2 mv squared, which just gives us radical 2gh. But the second part of this question is much more difficult. It's asking us for the velocity of the center of mass at the bottom of the incline if there is friction, which means it's rolling, which means we have to take into account KE rot. So we start in the beginning, sum of energy initial equals sum of the energy final. So we start out with PEG, and we end up with KE rot and KE trans. So it looks simple at first, because normally this I ends up canceling out with all the M's, but they left this as I, so it gets messy. So we have mgh equals 1/2 I omega squared plus 1/2 mv squared. And then what we can do is we've done this many times, v equals rho omega, rearrange, so omega squared equals v squared over r squared. So we sub that in for omega, and that gives us 1/2 I v squared over r squared. And because it's rolling without slipping, that v and that v are the same thing. So the reason that this is a difficult problem is because we have to get this v by itself, which is a mess. So the way that I did this was I multiplied through by 2, so bring the 2 over here. That gets rid of the halves on this side of the equation. And then I multiplied through by r squared. So that gives us an r squared here. It gets rid of the r squared in the bottom, but puts a new r squared over here. Now, at this point, all we have to do is divide through. You can think of this as factoring out the v squared. Divide through by the I and the mr squared, which puts that on the bottom. Then, square root of both sides, and that is our answer. In this question, we have a skater with no friction jumps on top of this board, and then the board and the skater are going to rotate and translate. So the question, it says, which of the following occurs? And they give you some choices here. But the first thing that you should think of is that there's no net external forces. There's no friction, there's no axles, there's no hinges. So if that's true, then linear momentum is conserved. There's also no net external torques, so angular momentum is conserved. So that's our answer. Linear and angular momentum are both conserved. In this final question, we have a couple of blocks and a pulley that has mass, and they want to know the equation for the acceleration of this pulley. Well, normally we would do this whole thing as a system to solve for alpha, but in this case they gave us T1 and T2. So think about this as a diagram from the perspective of the pulley. We have a force of tension 2 acting in this direction, trying to pivot it this way. And then we have another tension, Ft1, which I called negative. And those are both acting at radius r. So we just do a net torque equation. Net torque is I alpha. We sum up our torques. So we have I alpha equals, the first torque is RT2, minus, because the other torque is in the other direction due to the force of tension, and then we just factor out the r, and that gives us our answer of I alpha equals 2 T2 minus T1, all multiplied by r.